The operator had done everything correctly. He flew the Orlan-10 reconnaissance drone at low altitude, following the tree line east of the Ukrainian position to keep a low radar coverage. He had waited for the clouds to reduce optical observation. He had kept his transmission brief to avoid direction finding. His electronic warfare unit had the area blanketed in frequency jamming emissions across the standard control and video bands. And then the missile appeared. It came from the south at something above Mach 3. He had approximately 1.3 seconds between visual acquisition and impact. 3 tungsten darts released from the carrier and hit his aircraft before the carrier's second motor had finished burning. The drone did not evade. The drone did not detect an incoming radar lock. The drone did not receive any warning at all, because the weapon hunting, it was not using radar. It was not using infrared. It was not using radio frequency of any kind. It was riding a laser beam. The operator could not have jammed it. His unit's electronic warfare equipment, which was correctly deployed and correctly operated, was producing exactly the right jamming output for radio-controlled weapons. Against a missile guided by a thin pencil of laser light that does not interact with radio frequencies at any wavelength, that output was irrelevant. The Volnarez system beside him was perfectly functional and completely useless. The weapon that killed the Orlan was the Starstreak HVM. It entered British Army service in 1997. It was designed to fight Soviet helicopters over the North German plain during a war that never happened. The British Army is not currently the primary operator of the system. The Ukrainian 1129th Anti-Aircraft Missile Regiment is. If you're enjoying this story so far, don't forget to hit the like button and subscribe. Drop a comment telling me where in the world you're watching from. I love hearing from you. To understand why a missile designed in the 1980s for a Cold War scenario is now the most electronically difficult weapon in the Ukrainian air defense inventory, you need to understand what the electronic warfare environment in Ukraine actually looks like and why it has made almost every other short-range air defense system significantly harder to operate. Russia entered the full-scale war in February 2022 with some of the most extensive tactical electronic warfare capabilities of any military. Vehicle-mounted systems, including the Volnarez and Lezachek, specifically designed to counter small drones, create localized jamming bubbles that disrupt control and video links within several hundred meters of protected positions. Broader area denial systems like the Zittel R330ZH and elements of the Krasuka family can degrade GPS signals and communications across wider zones. By 2024, according to open-source intelligence tracked by defense researchers, Russian electronic warfare deployment had intensified to the point where Ukrainian FPV drone operators were reporting significant degradation of effectiveness in many sectors of the front. Hit rates for radio-controlled FPV drones that Ukrainian operators estimated at 40 to 60% in favorable conditions during 2023 reportedly dropped to 20 to 30% or lower in heavily jammed areas. The Ukrainian response to radio frequency jamming followed a predictable escalation cycle. Ukrainian drone developers upgraded control links to frequency-hopping spread spectrum radios that switch frequencies rapidly to evade narrowband jamming. They added directional antennas that concentrate signal toward the target area, increased transmission power, and introduced encrypted digital video links. Russian electronic warfare operators countered each upgrade in turn. New jammers appeared against new radio links on timelines measured in weeks. Both sides spent 2023 and 2024 in a continuous arms race that had one physical constraint the attackers could not overcome. Radio frequency countermeasures have a fundamental limitation from the attacker's perspective. As long as a weapon depends on a radio signal, the defender can always build a louder jammer. The laws of physics favor the jammer, because the jammer is close to the drone while the operator is kilometers away, and signal strength decreases with the square of the distance. Ukrainian FPV drone unit Typhoon described the experience to journalists as a hidden battle in the electromagnetic spectrum, one that made drone warfare exceptionally demanding and produced frequent sudden losses with no visible cause. A drone operator would have normal controls and normal video feed, and then suddenly the controls were dead and the feed was out and the drone was gone. This was the environment in which Ukrainian air defense systems were operating. Any weapon that depended on a radio frequency link faced the same physics problem that the FPV operators faced. The counter to this electronic environment was fiber optic drones, which tethered the operator to the aircraft through a glass cable rather than radio frequency, making them immune to RF jamming at the cost of limited range and operational complexity. That solution works for offensive weapons. It does not work for surface-to-air missiles, which must travel kilometers from the launcher to the target and cannot trail a cable behind them. Most short-range surface-to-air missiles in the current inventory of any army rely on one of three guidance methods: infrared homing, radio frequency command uplink, or GPS/satellite navigation. Russian electronic warfare can interfere with all three. Infrared jamming systems on aircraft and helicopters have existed for 50 years. RF command uplinks can be targeted by the same jamming equipment, disrupting Ukrainian drones. GPS spoofing and denial is a standard feature of the Russian electronic warfare suite. A missile using any of these guidance methods is, to varying degrees, vulnerable to the electronic environment that Russia has deployed. The Starstreak uses none of them. The Starstreak HVM uses laser beam riding guidance. The principle is straightforward. The fire control unit projects two low-intensity laser beams toward the target. The missile has sensors in its tail that detect these beams. Onboard computers compare the missile's position relative to the beam geometry and generate steering commands. The missile flies inside the beams until it reaches the target. There is no radio signal between the operator and the missile after launch. There is no RF uplink to jam. There is no infrared seeker to confuse with flares. There is no GPS input to spoof. The guidance signal is light, and the only way to interfere with the laser guidance link is to physically block the line of sight between the launcher and the target, which Russian electronic warfare equipment is not designed to do. Thales, the missile's manufacturer, describes the laser beam guidance as completely unjammable by conventional countermeasures. That description is accurate. The physical principles of the guidance system make it immune to the entire category of electronic warfare that Russia has deployed in Ukraine. All of it, the Volnares, the Krasuka, the GPS denial systems, the frequency hoppers, none of them interact with the Starstreak's guidance in any way that matters. The missile's warhead design compounds this guidance advantage. The Starstreak does not carry a conventional explosive warhead. It carries 3 tungsten alloy darts, each weighing 0.9 kilograms, loaded with 450 grams of PBX, 98 explosive. These darts are released from the carrier after the second stage motor completes its burn, approximately 400 meters from the launch point. The 3 darts spread in a pattern that increases the probability of at least one striking the target. Each dart has an impact delay fuse, meaning detonation occurs inside the target structure rather than on its surface. The combination of high-density tungsten penetration followed by internal detonation is specifically designed to defeat the countermeasures that Soviet helicopter designers had built into their aircraft. Armor plating on Heinz cockpit and engine compartment was proof against 12.7 millimeters rounds. 3 tungsten darts detonating inside the airframe was a different problem. Against the Orlan 10 reconnaissance drone and similar Russian UAS targets, which carry no armor at all, the effect is immediate and total. A single dart striking the airframe destroys it. 3 darts arriving within milliseconds of each other guaranteed destruction. Russian drone operators who recover debris from Starstreak engagements find wreckage consistent with multiple simultaneous penetrations, which in the field analysis produces a different debris pattern from a conventional warhead detonation. The Starstreak leaves a specific signature on its targets that experienced analysts can identify. The Russian military has had no difficulty determining which of its drones were killed by the British system. This was not an accident of design. It was a deliberate choice made in 1984. The origin of the Starstreak sits in a specific institutional problem that the British Army of the Rhine identified in 1980. Soviet doctrine for attacking NATO positions in West Germany relied heavily on low-flying helicopters and fast jets operating below radar coverage, using terrain masking to approach British and NATO positions before engaging ground forces. The Mi-24 Hind, which became the signature Soviet attack helicopter of the late Cold War, was designed to deliver firepower at low altitude against NATO armor formations. Its pilots were trained to fly at 15 to 30 meters above the terrain, using hills and tree lines as cover until the moment of attack. Against such targets, radar-guided missiles had detection problems. Against such targets, infrared-guided missiles faced a specific challenge. The Mi-24 carried UV-26 flare dispensers as standard defensive equipment, and Soviet pilots were trained to deploy them aggressively at the moment of missile launch. The existing Rapier missile system provided NATO point defense but required a relatively large footprint, was not easily integrated into forward armor formations, and had performance limitations against the very fast, very low targets that Soviet doctrine was optimizing for. The Bayer's appeal to the Ministry of Defense produced General Staff Requirement GSR 3979, which specified 3 launch platforms for a new high-velocity missile, a self-propelled vehicle launcher, a lightweight multi-round launcher, and a single-round man-portable launcher. The system had to protect forward-deployed armor from helicopters at close range with minimal warning time. It had to be fast enough to engage targets that conventional missiles would struggle to track. And it had to resist countermeasures, because Soviet helicopter pilots and their aircraft would be equipped with a full range of Russian EW and decoy systems. In 1984, the Ministry of Defense awarded a definition study contract to 2 competing teams, British Aerospace and Shorts Missile Systems in Belfast. By 1986, Shorts had won the contract. The missile that emerged from their work used laser beam guidance specifically because Soviet helicopters carried infrared jamming and flares as standard equipment. A missile that relied on heat-seeking guidance would be defeatable. A missile guided by light was not. The decision to use laser beam riding was not a technological experiment. It was the answer to a specific operational problem. Shorts Missile Systems, which became Thales Air Defense, built approximately 7,000 Starstreak missiles over the weapon production run. The system entered British Army service in 1997. It saw limited operational use in British hands. The Soviet helicopters it was designed to destroy never came. In 2011, Thales won the contract for the lightweight multi-role missile, a newer weapon designed for the Royal Navy's Wildcat helicopter. As part of restructuring production commitments, Thales announced it had agreed with the Ministry of Defense to redirect previously contracted budgets toward the new missile. Starstreak production effectively ended. The British Army maintained its existing inventory. The missiles remained serviceable, and no replacement procurement was initiated because the threat environment that justified the weapon, mass Soviet helicopter attack on NATO positions, had ceased to exist with the Cold War. What Britain transferred to Ukraine in April 2022 was therefore a finite stock, not an active production line, but an inventory of missiles built for a war that never happened. Sitting in British storage for 3 decades, now we'll fight a different war against a different adversary with the same guidance physics. The Ministry of Defense in 2022 committed to sustaining and maintaining the transferred systems. BAE Systems and Thales have both maintained operational involvement in the weapons through the war. But the fundamental constraint on Starstreak employment in Ukraine is the same constraint that limits every aspect of British military aid. The stock that exists is the stock that exists. This makes the 70-kill record of the 1,129th Anti-Aircraft Missile Regiment all the more significant as a per missile efficiency figure. 70 confirmed kills from a system operating on a finite missile stock, in conditions where replacement production is not straightforward, represents a discipline of employment that the Ukrainian operators have clearly developed. Missiles are not fired at marginal targets. Engagement are taken at ranges where the probability of kill is high. The result is a kill record that reflects both the guidance system's inherent reliability and the operator's learned discipline about when to use it. If you have watched this far, you already understand where this is going. The weapon built to fight Soviet low-flying threats is now fighting Russian drones, and the guidance system designed to defeat Soviet countermeasures is defeating Russian electronic warfare. Subscribe now if this is the kind of history that deserves to be told. It costs nothing, and we will be here when you come back. The United Kingdom announced a transfer of Starstreak systems to Ukraine in April 2022, approximately 2 months after the full-scale invasion began. Defense Secretary Ben Wallace confirmed the decision, describing the system as defensive in nature and capable of improving the defending force's ability to protect Ukrainian skies. The initial transfer included Stormer HVM vehicles, the self-propelled platform that mounts the Starstreak launcher on a modified Alvis Stormer armored personnel carrier, alongside shoulder launch units and associated Starstreak missiles. The Stormer is a tracked vehicle that can carry the Starstreak launcher across terrain that wheeled vehicles cannot access. Its thermal imaging system allows target detection at up to 18 kilometers, well beyond the missile's 7-kilometer kill range, giving the crew time to track, classify, and engage a target before it closes to dangerous proximity. Each launcher accommodates 8 ready Starstreak missiles with a total of 12 available, including reserves. Later British transfers added Martlet lightweight multi-role missiles, which use the same launcher systems as the Starstreak and provide engagement capability at ranges up to 9 kilometers. The Martlet uses laser beam guidance by the same physical principle as the Starstreak, carrying the unjammable laser guidance into a smaller, cheaper missile optimized for lower-value targets like reconnaissance drones. The complete interoperability between Starstreak and Martlet from the same launcher platform means Ukrainian crews can select the appropriate missile for the specific threat without switching systems. An Orlan 10 reconnaissance drone at 4 kilometers gets a Martlet. A larger, faster, higher-value target gets a Starstreak. The launcher handles both. The Ukrainian crews who received the system required approximately 1 month to reach operational proficiency, according to accounts published by Militarnyi. This training period was conducted partly in Britain and partly in country. Crews who came from Soviet-era air defense systems noted that the Starstreak's manual tracking requirement, where the operator must keep the launcher pointed at the target throughout the engagement, was a learned skill distinct from the auto-tracking systems of Soviet surface-to-air missiles. The combination of manual tracking and laser guidance places the engagement outcome almost entirely in the hands of the operator. A skilled operator produces consistent results. A novice operator produces missed shots. The 1-month training program is designed to build the tracking skill to the point where the laser guidance system's inherent accuracy can be reliably achieved. The 1,129th Anti-Aircraft Missile Regiment, which operates the British systems, published a detailed account of their results in 2024. The unit had, at that point, destroyed 70 air targets in 2 years of full-scale war. Zala reconnaissance drones, Supercam surveillance platforms, Orlan 10 and Orlan 30 multi-role drones, and Merlin VR vertical takeoff reconnaissance systems. The operator quoted in the account described a specific advantage. The laser-guided missile does not need a lock on a target by thermal signature, works day and night, and performs in any weather condition that allows visual acquisition of the target. That last phrase is a limitation. The Starstreak requires the operator to maintain visual tracking of the target and keep the launcher aimed at it throughout the engagement. Poor visibility, heavy smoke, or obscured target acquisition will degrade performance. The missile is also optimized for subsonic and relatively slow targets at close range. Ballistic missiles and supersonic aircraft at high altitude are beyond the system's design envelope. The Stormer HVM Starstreak complements Ukraine's layered air defense rather than substituting for its longer-range components. Within its designed envelope, however, it performs with a reliability that the Russian electronic warfare environment cannot reduce. If you're hooked on this story, make sure to subscribe and turn on notifications so you never miss an upload. Your support means everything and helps me bring you more emotional stories like this one. The Russian drone inventory that Ukraine is primarily defending against consists of systems that operate at altitudes and speeds where the Starstreak's engagement parameters are well suited. The Orlan 10, the most common Russian reconnaissance drone, has a maximum speed of approximately 150 kilometers per hour and typically operates at altitudes of 500 to 3,000 meters. The Shahed 136 loitering munition that Russia began using in mass night attacks from September 2022 has a cruising speed of approximately 185 kilometers per hour and flies at altitudes often below 1,000 meters. The Lancet kamikaze drone, which Russia has used extensively against Ukrainian armored vehicles and artillery, flies at approximately 130 kilometers per hour. All of these are within the Starstreak's 300-meter to 7-kilometer engagement envelope. All of them are traveling at speeds where the missile's Mach 3.5 to 4 velocity provides overwhelming closure rate, giving targets less than 2 seconds of warning at typical engagement distances. and all of them rely on radio frequency control links that are entirely invisible to the Starstreak's laser guidance system. The missile does not see their signals. The missile does not care about their signals. It sees a target. It rides a laser. It arrives. Ukrainian operators have adapted the Starstreak's employment to the specific characteristics of Russian drone operations. The Stormer HVM's thermal imaging system allows target acquisition against the Orlan 10 at ranges where the aircraft's small radar cross-section would make radar tracking unreliable. The same thermal imager that finds a drone by heat signature feeds targeting data to the laser guidance system that the drone cannot detect or defeat. The drone operator receives no warning. His EW equipment generates no countermeasure. The first indication of the Starstreak's presence is the impact. One of the Stormer HVM operators in the 1129th Anti-Aircraft Missile Regiment described the engagement process in terms that the technical specifications alone cannot capture. The operator noted that the Russian Orlan 10 drones the regiment was targeting were flying at altitudes and speeds that made them manageable targets for the Starstreak's tracking requirements. The drone flies in a relatively predictable pattern at relatively constant altitude. A trained operator can maintain the laser guidance cross on the target through the short duration of the missile's flight. What the operator found notable was not the difficulty of the engagement, but the absence of any response from the drone. Infrared-guided missiles sometimes cause pilots and drone operators to deploy countermeasures, a flare dump, a sharp maneuver, and altitude change. The Starstreak produces no such response because the drone's threat warning systems detect nothing. The drone continues on its course until the 3 tungsten darts arrive. Russia was sufficiently concerned about the Stormer HVM's effectiveness to task Lancet loitering munitions specifically against the systems. In March 2023, Russian forces destroyed the first confirmed Stormer HVM in Ukraine using a Lancet strike on the vehicle itself. The engagement was filmed from a second Russian drone monitoring the battlefield, and the footage showed the Lancet impact between the Stormer's chassis and turret. Ukraine's response was to introduce mock-up decoys of the Stormer HVM, deploying visual copies of the system in November 2024, confirmed by Militarny reporting. The decoys draw Russian drone attacks onto non-functional targets while the operational vehicles operate nearby. The fact that Ukraine devotes production resources and operational management to a deception program protecting the Starstreak indicates the value its users have assigned to the system. A weapon that does not produce results does not get protected with fakes. The comparison with other short-range air defense systems in Ukrainian service illustrates the Starstreak's specific advantage. The American Stinger man-pads, which Ukraine operates in large numbers, uses passive infrared guidance. It is faster than the Starstreak in terms of reaction time for a dismounted operator and highly effective against aircraft with significant heat signatures. Against modern Russian drones, which are typically piston engine or electric propulsion systems with limited thermal signatures, the Stinger's infrared seeker faces acquisition challenges that the laser-guided Starstreak does not. The Russian abdo-base and repellent jamming systems also generate broadband RF interference that can affect some Stinger variants' proximity fusing. Ukrainian-operated man-pad systems of Soviet origin using infrared guidance face similar constraints, compounded by aging components and limited missile reserves. The French Crotale and SAMP/T systems that France has supplied operate at ranges and altitudes suited for medium-altitude threats, but require significant setup time and fixed or semi-fixed positioning that exposes them to Russian counter-battery fire. The Starstreak, mounted on the mobile Stormer platform, combines the Scimitar's mobility advantage with the guidance and vulnerability that no other system in Ukrainian inventory replicates. The Stormer vehicle fires, displaces, and repositions before Russian counter-battery systems can respond. The Starstreak missile, already in flight, cannot be recalled or diverted by Russian EW. The guidance link between the launcher and the missile travels at the speed of light and cannot be blocked by equipment that operates in the radio frequency spectrum. The Russian electronic warfare operators who monitor Ukrainian air defense communications, who track radar emissions, who flood control frequencies with noise, have nothing to do when a Stormer HVM is operating. There is nothing in the electromagnetic spectrum to detect. There is nothing to jam. There is no signal to find. The engineers at Short's Missile Systems, who worked through the 1980s designing a weapon for the Cold War, never modeled a drone swarm environment. They were solving a 1984 problem. Soviet Me. 24 Hind helicopters approaching NATO positions at low altitude. Their pilots carrying radar warning receivers and flare dispensers. Their aircraft surrounded by infrared jamming fields. The answer to that problem was laser guidance. The answer turned out to apply with equal precision to a 2024 problem they could not have imagined. The Orlan 10 operator, whose drone was destroyed over the Ukrainian positions, had done everything his training required. He had applied his EW support correctly. He had followed the protocol that Russian doctrine prescribes for operating in a contested electromagnetic environment. It was not enough, because the weapon searching for his drone was not operating in that environment at all. The Starstreak does not jam. It does not broadcast. It does not generate an electromagnetic signature that Russian sensors can locate. A laser beam is invisible to radio frequency detection equipment. The operator's electronic support measures detected nothing because there was nothing to detect. The missile arrived and the drone was gone. An electronic warfare log from that engagement would show normal jamming output, normal drone signals, and then silence. That silence is what Russian drone operators in sectors where Starstreak is deployed have come to associate with the system. They know the signature now. A sector where Russian drones are being lost at a rate inconsistent with RF jammable weapons, where the standard countermeasures are not producing the degradation they produce everywhere else. The British missile does not announce itself. It simply works in conditions where other weapons do not, because the British engineers who designed it in 1984 were solving a Soviet problem and accidentally produced the answer to a Russian one. The 1,129th Anti-Aircraft Missile Regiment's 70 confirmed kills over 2 years represent the documented results from one unit. Ukraine has deployed Stormer HVM systems in multiple sectors, both for point defense of key facilities and for frontline protection of armor formations. The total Starstreak employment in Ukraine since April 2022 runs to hundreds of missiles across several units. The mock-up program for the Stormer HVM, confirmed by Militarny reporting in November 2024, required production resources and operational management that would only be prioritized for a system delivering genuine results. The Starstreak is not Ukraine's primary air defense system. The S-300 Patriot and Iris-T provide coverage at altitudes and ranges that the short-range Starstreak cannot reach. The Gepard self-propelled anti-aircraft gun provides volume of fire against saturation drone attacks that a missile system with limited reload capacity cannot match alone. Crow-Tal and SAMP/T systems cover medium-altitude threats. Ukraine's air defense is a deliberately layered structure, each component covering the altitude and threat category where its specific capabilities are strongest. The Starstreak occupies a specific layer in that structure: terminal defense against close-range, low-altitude threats in an electronic warfare environment designed to defeat every other guidance method available. It is the layer that Russia cannot electronically suppress. When a Russian drone penetrates through the outer layers of Ukrainian air defense, the Starstreak is what meets it at the end. And unlike the systems that came before it in the engagement sequence, the Starstreak does not face degradation from the electronic warfare environment that the drone has passed through to get there. The operational picture that emerges from 2 years of documented use is of a system that Russian commanders understand well enough to target specifically, that Ukrainian commanders value enough to protect with deception programs, and that Russian drone operators have learned to associate with unexplained losses in sectors where standard countermeasures are producing no effect. The system works because its guidance principle places it outside the physics of the problem that Russian EW is designed to solve. The Starstreak handles the targets that the EW environment makes hardest to engage for other systems, does so with guidance that the EW environment cannot touch, and does it at speeds that give targets no time to react even if they could. For the Russian drone operators flying in sectors where the system is deployed, the absence of any warning signal and the absence of any effective countermeasure produces a specific operational experience. They fly correctly. They apply their doctrine correctly. Their EW support functions as designed, and then the drone is gone. There is no record in the electromagnetic spectrum of what happened. There is only the debris. The Shorts engineers who built the first Starstreak prototypes in Belfast in the 1980s are retired or dead. The factory in Castlereagh, where Thales produces and maintains the missiles, has operated under several owners since the original contract. The British Army of the Rhine that wrote General Staff Requirement GSR 3979 was dissolved in 1994 after the Cold War ended and the Soviet threat it was designed to counter ceased to exist. The engineers who chose laser beam riding guidance over infrared homing made their choice because infrared guidance was defeatable by Soviet countermeasures. They were solving the problem they had been given. How do you build a missile that Soviet helicopters cannot confuse with flares? The answer was a missile that did not chase heat. The answer was light. That answer, arrived through Cold War threat analysis and 1980 propulsion engineering in a factory in Belfast, is now the most electronically resilient guidance principle on the Ukrainian battlefield. Not because the engineers predicted the drone war, not because they anticipated Russian EW proliferation, because they solved a physics problem about guidance immunity in 1984, and the solution has no expiry date. The weapon that requirement produced continued in British service. When Russia invaded Ukraine, Britain sent it. The Ukrainian crews who learned to operate it in approximately 1 month of training are now using it to defeat electronic warfare systems that did not exist when the missile was designed against drone threats that no one in 1984 imagined, in a war that the original requirement document never anticipated. The Soviet helicopter pilots who were supposed to be the Starstreak's targets never came. The Russian drone operators who became its actual targets did not know what they were flying into. They had every electronic advantage the modern battlefield provides. They had the most extensive tactical jamming capability of any military. They had systems specifically designed to defeat every category of guided missile in common use. The laser beam does not belong to any of those categories. It never did. If you stayed until the end, you understand why this story does not appear in the standard accounts of Western weapons in Ukraine. The Starstreak is not the most capable system. It does not have the range of Patriot or the firepower of IRIS-T. It is a short-range missile designed for decades ago for a war that never happened. What it has in the specific electronic environment that defines the war in Ukraine is something none of the newer, more expensive, more sophisticated systems can claim, a guidance principle that the entire Russian electronic warfare apparatus cannot touch. Subscribe and tell us where you are watching from. Tell us if you have served with the system or if this sent you looking for more. The comments section is where the people who know these stories add what the official accounts leave out. If this sent you somewhere new, we will be here. Thank you so much for watching until the end. If you love this story, check out the other videos on your screen now. I think you'll really enjoy them. And don't forget to subscribe if you haven't already. See you in the next story.